Okay, I have a physics problem for you based on my own real life. So you're driving around your car and you're coming up to a stoplight and you could just hurry up and get there and stop. Or you could kind of like go slow so that when you get to the stoplight and it turns green, you're still moving. So there's two options, right? When the light turns green, you're stopped, or when the light turns green, you're still moving. And let's imagine in this situation that I timed it perfectly, right? So I'm kind of coasting along and I get to the stoplight and boom, it turns green and I'm still moving. It's kind of hard to do, but I like to try to time that. Now imagine there's another car there that didn't do that and they were stopped. So I have car A, that's me, and at the stoplight, when it turns green, I'm going 10 meters per second. Car B, at the stoplight, when it turns green, is stationary at 0 meters per second. Now, suppose that I accelerate at 2 meters per second squared and car B is at 4 meters per second squared. So the question is, how far will the two cars go before they meet, and how fast will they be going? Okay, so we have a kinematics equation here. We have a kinematics problem, constant acceleration. So let me just write down the kinematic equation, one of the kinematic equations for car A. So I can write car A as XA is equal to x0 plus VA0t plus 1/2 AA t squared. That's my kinematic equation. Now, I put the velocity VA0 to be different. X0 is left as x0 because they're going to start at the same position, which I'm going to call x0. So they're going to start both at x equals 0. And then car B looks like this. It has that same x0, and it has a 0 initial velocity, so I'm going to put 0t plus 1/2 AB t squared. Now, notice that they both are moving in the x direction, and they both change position with respect to time. Let's kind of sketch out what both of these trajectories would look like in space. So imagine that I make a graph of position as a function of time. So for car B, it starts at x equals 0 with a 0 velocity. So this is just x is 1/2 AT squared. That's just a plain parabola. I can sketch that. It would look like this. Parabola. Now for car A, it's a little bit different, right? Because it's going to start with some velocity. So this one has a 0 velocity. The slope of the line is 0 at the beginning, but that one will not be 0. And in fact, it's going to be some positive value, but it's not going to be paraboled as much because the acceleration is lower. So maybe it looks something like this. So this is car A, and this is car B. And I want to find that point right there where they meet. So that's some x value and some t value. They have to have the same x and the same t at the same time. And so there's my equation for x as a function of t for the two cars. So that's my graph. And I want them to have the same x value. So I want to find out when xa is equal to xb. So I can set these two right-hand sides equal to each other. So let's do that. I'm going to go ahead and put in 0 for x0 up for both of those cases. I get VA0t plus 1/2 AA t squared equals, this one is 0, 0, just going to be 1/2 AB t squared. So now I have an equation with just one variable in it, and that one variable is time. Now, it's possible you could have solved this for time and plugged it in down here. That would still work. But when you see something that's set up like that really easy, just go for it. Go for the easy thing. Okay, I want to solve for time. I have a t squared, t squared. So let's divide both sides of the equation by t. And at the same time, I have this 1/2. So I'm going to multiply both sides by 2 over t. So this is going to be 2 over t, both sides. And that way we'll get rid of that t, we'll get rid of the t squared, and we'll get rid of the 2's. So over here I get 2 VA0, and the t's canceled, plus 2 times 1/2 is 1. AAT equals ABT. I'm trying to solve for t, so let's subtract this from both sides. I get 2va0 equals abt minus aat, and I can factor out the t, so that's ab minus aat. I can solve for t by dividing both sides by that, and I feel like I'm running out of room. I'm going to erase this stuff right here. It doesn't look linear anymore, but I can do that. So I get VA0 is going to be equal, no, t. I'm solving for t. T equals 2VA0 over AB minus AA, and that's that. And let's just check, right? Let's just think, does this have the correct units? So this has units of meters per second. These have units of meters per second squared. So meters per second divided by meters per second squared. The meters cancel. The 1 over seconds divided by 1 over seconds squared gives me seconds, which is time. So that's good. Let's put in our values. I have 2. My initial velocity is 10. Here I have 4 for the acceleration for B, minus 2, the acceleration for A. 4 minus 2 is, you got it, is 2. And so now we get 2 over 2 cancels, I just get 10. So 10 seconds. It takes 10 seconds for the two cars to meet. So let's put that up here. T equals 10 seconds. But I didn't care about when they meet it. I want to find out where they meet. What's the x value? Okay, so let's erase this. Remember, they have to have the same position at the same time. So I can take either one of these equations, plug in my value for t, and I should get the answer. This one's easier, so I'm going to go ahead and do that one. So xb, I'll go ahead and write it that way, is 1/2 abt squared. So that's 1/2 times ab, which is 4, times t squared, 10 squared. So here I have 1/2 times 4 is 2. 10 squared is 100. So I get 200 meters. So that's this position where they meet, 200 meters. Now, if you want to check, you can check by putting in the same time up here. I'm not going to do that. The second part of the question was, how fast are they going? Now, there's two ways to answer this. I'm going to show you the first way and tell you the other way. Now I can use another kinematic equation. For A, it looks like this. VA is VA0 plus AAT. So if I know the initial velocity, I do. If I know the acceleration, I do. And the time, I do. I can put it in. I get 10 plus 2 times 10. So 2 times 10 is 20, plus 10 is 30. If you put that in your calculator, I'm not going to judge you. You do you. Okay, I can do that in my head though. 30 meters per second. Now, these cars do not have the same speed, they have the same position. So let's find the car B. It's going to be its initial velocity 0 plus its acceleration times time. So that's going to be 0 plus 4 times 10, which is 40 meters per second. So this car is going 40, you can see the slope is greater, and that one's 30. It has to be going faster in order to catch up to it, right? And there you go. Now, what if you didn't like that method? You could actually use the other kinematic equation, VA squared, VA0 squared plus 2AA times XA minus X0. This is that other kinematic equation that does not have time. So you can plug in your value for your initial velocity, your acceleration, your change in position, and then you could do it this way too. You should get the same thing. Okay, so there you go. Physics problem, real life physics problem.